Okay. So we define trace on positive operators. Okay. Started recording this. We defined trace on positive operators. So this is trace is a function from B of H plus positive operators taking values in 0 to infinity. Then we defined B1H trace class operators. Oh, sorry. Why is it? I will erase it. One second. This, yeah, it should be like this. Now it should be okay. So we defined trace from B of H plus to positive, extended real line, extended positive real line, 0 infinity on positive operators. And we defined B1H to be all those operators T in B of H. This is not what we defined, but we later defined that this is equal to, okay. So we define T greater than or equal to 0. We defined this to be this span of T greater than 0 and trace of T less than infinity. This is exactly equal to T in B of H, trace of mod T, okay, is less than or equal to infinity, where mod T is equal to T star T, the unique square root of T star T. Okay. So we defined Hilbert-Smith operator also, but more or less we have finished that. So anyway, I will recall. We defined Hilbert-Smith operator is equal to all those T in B of H such that trace of T star T is less than infinity, which is same as T in B of H summation norm Ten square is finite. It can be for all En or for, if it is true for one single orthonormal basis, it's true for all orthonormal basis. So it's enough to take one single orthonormal. This is what B2H. Then we defined an inner product on B2H, which is defined as ST equal to trace of T star S. Okay, you can define ST star also. Both are same anyway. We will show that both are same. So we define this, and this is a genuine inner product. That's what we have. Okay. So now we prove the following proposition, which is called tracial property. We have defined something called trace, and we want to make sure it is actually a trace. It satisfies the tracial property. Tracial property is the following. If first we have to make sense of the product, so the product should be a trace class. That will be always the case. It may not be a trace class. It may be in Hilbert-Smith, but if you take product of two Hilbert-Smith operator, that's again Hilbert-Smith operator. So trace of ST. Yeah. We can product of Hilbert-Smith operator is not Hilbert-Smith. I'm sorry. If you take product of two Hilbert-Smith operator, then the product is trace class operator. Okay. That's what we have verified earlier. So S is in B2H. T is in B2H. Trace class is contained in Hilbert-Smith, and the Hilbert-Smith operator need not be trace class. Okay. But then if you take product, it is like you can, the analog is between L1 and L1 and L2. Trace class operators are like L1 and Hilbert-Smith operators are like L2. So if you take product, pointwise product of L2 functions or L2 sequence, then it's an L1 sequence. So that that is the analog of this. then the trace of ST, which we can make sense. S is a Hilbert-Smith operator, T is a Hilbert-Smith operator, the product is a Hilbert-Smith operator. So this is equal to trace of TS. That's all. So this is for Hilbert-Smith operator. For T in B1H, and S can be anything in B of H. Of course, the product is, we know that trace class operators form an ideal. So because of that, trace, you can make sense of trace of TS or ST, whatever. So that is equal to trace of TS, ST. Trace of TS equal to trace of ST. Okay. So this is what is called tracial property. So notice that this is not commutativity. I mean, it is not something like trace of, if you have three operators, STR, then you can, this is equal to trace of, you can write it as RST. It's not that you can't bring the R in the middle. Okay. So you can only do this. Okay. I mean, it's like you can take one of this as this and this, and you can bring the R this side and you can write ST like this. You can bring the T this side. This is also equal to trace of TRS. Okay. But you can't bring this S between R and T and R. Okay. So this is not commutative. Commutative means you can insert the operator anywhere you want, but that you can't do in multiplication. In a sentence of if you have a multiplication expression, then you can take any operator anywhere. I mean, any element anywhere in a commutative setup. But this is not commutative. This is not nothing to do commutative. It's just you can have a circular action. I mean, cyclic action. Okay, something, whatever it means. Okay. Okay, so this is the property we want to prove. So we want to prove trace of ST equal to trace of TS for Hilbert-Smith operators. So we know that this is an inner product. Okay, is an inner product. This is equal to trace of T star S. T star S, no? T S equal to S star T. ST equal to this. So what is this? That is equal to T star S. T star S is inner product on that. So we want to use inner product satisfy Cauchy-Schwarz inequality. Inner product on B2H. So now we have S and T, and we want to no, not Cauchy-Schwarz inequality. Inner product satisfy what are called polarization identity. We want to use the polarization identity. The reason for using polarization identities, we will get an S plus T and we can interchange them. So this is what we will do following. So we have the following. If you take any inner product satisfy this. In particular, this inner product. This is equal to 4 times. What did I do? 4 times ST is equal to summation. You can write it in terms of some sort of norm. So which is equal to K equal to 0 to 3 I power K S. So S plus I power KT. S plus I power KT. Okay, I don't want to write it as norm because you have to take the square and square root to something. So you can write it as norm if you want, but I write it like this. Okay, this is the polarization identity. Okay, this is the identity. Okay, so but here what do we want? But this is, so this is equal to trace of T star S, right? T star S equal to, this says T star S equal to summation K equal to 0 to 3 I power K trace of. So I mean, we want to prove trace of TS equal to trace of ST. We can, it's enough if we prove trace of T star S is equal to trace of ST star. Okay, because star, it's closed under star, so it's okay. Okay, so trace of this. So now inner product between this. Trace of S plus I power K. The star is, So the star should be on this s power I power k t star s plus I power t, right? I power k. Okay, this is okay.
There's a 4.
This is okay.
No, there's a 4 in the left.
There is a
4.
four. Okay, 4 is there. Okay, 4 is just dummy 4. You will get it back. Okay, so that's not okay. So other than that, I mean, I should make mistake here. Okay, then it will be a problem. So it's okay. So then now we know that trace of tt star equal to trace. I mean, we have already proved that this property we have proved. Trace of any a star equal to trace of a star a. Okay? So I will use that property which we have proved. So here it is in that form. A star a is in that form, which is equal to trace of a star. So that is equal to summation k equal to 3, k equal to 0 to 3, I power k. Trace. I want to take the star of this thing. So which is s plus I power k t star. What is that I'm doing? So I'm sorry. I want to just bring this here. No, I just have to bring it here. I mean, this is my A, that is my A star. So A star will go there, and so this is just equal to S plus I power K T star. Okay. Okay. So this is equal to summation K equal to 0 to 3. Now this I can write it as I power K trace. So I want to bring a star there. So S star plus I power minus K times T star whole star. Okay, I can take a star inside and star outside, which is without star. So here also I do the same. Here I just take the star inside. S star plus I power minus K T star. Okay. Okay. Now this is equal to summation K equal to 0 to 3. I power K remains as it is. Trace. Then this is T star. This I power minus K, I can take it here. I power K times S star. And the bottom there will be an I power K. Okay. I mean, this denominator, there's an I power K. And then, but then I power K with, I mean, it has to be I power K, but because of the star, it will become I power minus K. That is equal to, here it will be S star. So here it is again. T star plus I power K S star.
The first term has also star,
Say it again.
a whole bracket star for the first term.
Here,
Next line.
here.
Yeah.
Huh?
Yeah. So it is T star plus I power K S star whole star.
No, I'm just taking, yeah, there is a star outside. Is that what you, oh, sure. There is a star outside. Yeah. I have only taken the I power K this side. That's all. The star outside, but then in the denominator, I take the star and that become I power minus K. Okay. Yeah, you are right. Yeah, I missed that star. Now this I power minus K and that will cancel. So this is just equal to K equal to 0 to 3 I power K trace of 3. So this is just the inner product. I will just this is just the inner product of T star plus I power K S star T star plus I power K S star. Now this is equal to 4 times, sorry, trace. I mean, this is just the inner product between T star and, I mean, what is the inner product there? So I'm supposed, how is it defined? The inner product is defined as, so we started with inner product ST. Okay, so now this is T star S star. Yeah. Trace of ST star. That's what you want. 4 times. So we started with trace of T star S, and we have got trace of ST star. Okay. So this is for Hilbert-Smith operator. I mean, there's nothing. I have used the polarization identity, but I have to use some property of trace. I have used the property of trace of TT star equal to T star T. Okay. Then it is in that form. So I can interchange and then get this back. That's all. Is anyway easy exercise. If you go through it, you will get it. Okay. Okay. So this is true for Hilbert-Smith operator. T and S are Hilbert-Smith operators. Okay. Now, suppose T is in trace class. So T is in B1H. B1H and S is in B of H. Okay. Then trace of TS. So no, first we can, I mean, we have to prove that, we want to prove that trace of, then we want to prove. Trace of TS equal to trace of ST. Okay. So now it's enough to prove, because we know that B1H is a span of positive trace class operator, enough to prove for T greater than or equal to 0. We assume T is greater than or equal to 0. So then trace of ST is equal to trace of ST power half, T power half. Okay. Now if T is in B1H, then by definition, T power half is in B2H. Okay. I mean, the definition of B2H is something is in T is in B2H if T star T is in T1H. But then T power half, T power half star is T power half. T power half, E power half, you will get this T. So for positive operators, you can take the square root, that is in Hilbert-Smith. And also, Hilbert-Smith is an ideal, we have proved. So ST power half is also in B2H. Okay. So because of this, this is equal to trace of T power half. I can bring one T power half here by using this. Okay. T power half, ST power half. Okay. Now I can use these two. Right? What do you want to do? No, that will be the same thing. That will be go back. Now I want to use this and this. Okay. So that is equal to trace of T power half, S. So trace of TS. Okay. That's all. Is it clear? Maybe my handwriting is very bad. That's all. So we apply the earlier lemma for two Hilbert-Smith operator, T power half and ST. I mean, earlier, whatever we have proved, T power half and ST power half, and we get this. Hope it's clear. Okay. So if you want me to write anything again, you tell me. I hope everything is readable, even though it's not looking good. Okay. Any question? There is. Okay. So I go to the next most important theorem, proposition. The proposition is the following. Norm 1, norm T1. T in B1H, norm of T1 equal to trace of mod T. Defines a proper norm, defines a norm on B1H, and B1H is a Banach space. Banach space. Okay. So this is the theorem we want. So okay. So we want to prove that B1H is a Banach space with respect to this norm. Of course, it's not a Banach space with respect to operator norm because the closure will be all compact operators. So towards proving this, I want to prove a lemma. For T in B1H, for T in B1H, and S is in B of H, okay. Trace of ST mod is less than or equal to, so S is in B of H, norm S times trace of mod. Oh, actually, I want to prove something more further. Maybe I will. Defines a norm. Okay, defines a norm. Further, B1H is a Banach algebra. It's not just a Banach space. Banach algebra means it's a Banach space. Means that is B1H is a Banach space. And the norm of TS, the one norm. This is this inequality is satisfied by operator norm. Norm of TS is less than or equal to norm T times norm S. So the same thing is satisfied here. Okay. So this is what is called Banach. I mean, this is this inequality for Banach algebra inequality is this. Okay. So this is what I mean by it's a Banach algebra. So it's a Banach space, and further it's an algebra. You can multiply to, I mean, it's an ideal. So in particular, it's an algebra. You can multiply to, it's a ring. You can multiply two operators, and that is in trace class. That's also a trace class operator. If you multiply two trace class operators, it's again a trace class operator, and they satisfy this inequality. This is a Banach algebra inequality. Okay. So I want to prove that. Towards proving that, I want this lemma. Okay. So T is in B1H, T, S is the interval. Okay. Proof. So here I want to use the Cauchy-Schwarz inequality of the Hilbert-Smith operator. So I want to use the Cauchy-Schwarz inequality, but then to use Cauchy-Schwarz inequality, there is no Hilbert-Smith operator here, right? So how do you get a Hilbert-Smith operator when you have a T and B1H? You have only B1H. You don't have a Hilbert-Smith operator here. I mean, you can't take T power half because it's not a positive operator. So because of this, we do the following. We can take the polar decomposition. Okay, then you have the mod T here, be the polar decomposition. It is because I want to use the Cauchy-Schwarz inequality. To use Cauchy-Schwarz inequality, I need operators in B1H. So we don't see any operator which is in B1H. So I mean, but you can take the mod T. If T is in trace class, then mod T is also trace class. Mod T power half is Hilbert-Smith. So somehow we want to get that. So that is why we are using this. Be the polar decomposition. Okay. Then mod T is in B1H. Because T is in B1H, mod T is in B1H. So mod T power half is also in B1H, is in B2H. Okay. And also S T power half, T power S mod T power half. T power half is in B2H, this is also in B2H. So now we can apply the Hilbert-Smith, Cauchy-Schwarz inequality. We can apply the Hilbert-Smith inner product. I mean, we can apply the Cauchy-Schwarz inequality for the Hilbert-Smith operators for take these things. Okay, so this is the trace of ST. This is equal to trace of S U star mod T. Oh, sorry. This should be, anyway, I will come to this. Whatever I want to write here, I will write it now. U star mod T. Okay. Now this is equal to trace of S. See, we have already seen if if T equal to UT, U mod T is the polar decomposition, then we have already seen the last class. Then mod T is equal to U star T. Okay. Okay. That follows from the polar decomposition. U star acts as a isometry on mod T. So if you put a U before that, if you, yeah, what did I write? Oh, no. Why? Oh, no, I should have only U mod T. No, it's okay. Why did I bring U star T? No, it is just UT, no? Sorry, there is no U star T. I'm sorry. I got confused unnecessarily. This is okay. Yes, UT. This is okay, no? So please tell me if you are following.
Yes, sir.
This is okay? Okay. So I don't know why I got into the idea of U star. That will come later. I somehow got confused now itself. Okay. But later inequality, in the later proposition, we have to get it. So when we prove this Banach space, there I need this U star. No, it's okay. Yeah, this is okay. So SUT. So this is Hilbert-Schmidt. This is one operator. This is one operator. These two are in Hilbert-Schmidt. Okay. Whatever I have written in bracket. So they are Hilbert-Schmidt operator. So you can use that. You can use the Cauchy-Schwarz inequality. So to use the Cauchy-Schwarz inequality, I write it like this. So this first Hilbert-Schmidt is inner product something is less than or equal to now. This is the Hilbert. Cauchy-Schwarz is this mod is less than or equal to norm x times norm y. But this you can take the square and then you can take the square because the Hilbert-Schmidt norm you will get a square root and other things, right? So I write. So this is basically equal to trace of ST square. Okay. This is less than or equal to. This is equal to that. So this is less than or equal to. I'm just splitting it into these two operators. That is equal to the Hilbert-Schmidt norm of this SU mod T power half 2. Okay. Then there is a square here. Then T power half norm 2 square, right? So that's what I have written. So this is equal to trace of T power half T power. The Hilbert-Schmidt norm, Hilbert-Schmidt norm means you have to take the Hilbert-Schmidt inner product of the element with itself and take the square root. So T power half T power half whole square root will become square. So mod T power half mod T power half. There will be a square root that will go away with the square. Okay, again here. So I have to take the. But I want here it will be T power half mod T power half U star S star. Okay. Then mod T power half. Okay, this is okay. This is okay. I have just written the Hilbert-Schmidt inner product. Now this is equal to trace of mod T. So we have got that, and trace of mod T power half U star S star mod T power half. Now we have already seen this inequality. We have, if you look at the last class lecture, there we have proved that trace of any V star mod T. If you some positive operator, V star, maybe I will write it as AV. that A is greater than or equal to 0 and A is in B1H. Okay. This is less than or equal to norm of V star V times trace of A. Okay. We approved this in the last class. But anyway, this is very easy. When you want to compute this trace of V star AV, you have to expand it in an orthonormal basis like V star AV, EN. Okay. No, it's the other way. I'm sorry. No, what I said is not correct. So that's why we need to prove. We also have something else. This is what we have proved. A power half V star V A power half. If you have something like this, or you can have any positive operator here. Okay. Okay. This is less than or equal to norm of V star V. Oh, here I fuck. Oh, you didn't tell me. If I have U star, S star, and then I have a US also there. Okay. Now V star V times trace of A square. This we proved in the last class, if you remember. How we prove it? See, this is, maybe I will write it for that itself. I mean, this is equal to what? This is equal to trace of some A, V star V, A, En, not trace, summation. Okay. Okay. Now you can take the AEN outside. This is equal to summation V star V, AEN, right? Now this V star V is a positive operator. So this is less than or equal to norm V star V. This is not true for all operators. Less than AEN. Now you can bring that A this side and you get the A square. Okay. So because of this. So this we have done in the last class. I remove it because the same proof I went through in the last class. Okay. So because of this, that is less than or equal to trace of mod T into norm of that U star, S star, US, which is same as norm, I mean, norm square of that, which is same as C star identity, which is just same as norm of US square, okay, times trace of norm T. T power of is norm T. Now this is, but then norm US is less than or equal to norm U times norm S. So this is less than or equal to norm T times norm S square and this square. So this is equal to, okay. So we have proved the following. Oh, trace of mod, yeah, correct. Trace of mod. That's what we wanted. Yeah. This is what, so let me go through it again. Trace of, we want to prove, I mean, this is something like this. You are proving that trace of ST mod of this is less than or equal to norm S times trace of mod. Okay. So if you have a L1 sequence, some sequence, summation, some xn, some lambda n. Okay, this lambda n, this S is in B of H in S is like something in L infinity. Okay, then this is less than or equal to this infinity norm of this. That is this supremum of lambda n, mod lambda n. And then you have summation mod xn. This is just the L1 norm of lambda. L infinity norm of lambda times x norm of 1. Okay, if x is the sequence xn, lambda is a sequence lambda n, then this is clear for a L1 sequence and an L infinity sequence. But then we cannot do like that in a Hilbert space, because see, if we have one single operator T of which is a trace class operator, that is like a L1 sequence. Okay, I mean, it's not true about the bounded operator, but you have a L, if you have a one single trace class operator, and that looks like an L1 sequence. So if, but then I mean, it's not commutative also. If I mean, even if you have a trace class operator or something, even if you have S is a compact operator, then it may be diagonalizable with respect to a different orthonormal basis. So you cannot use the technique you have used in sequences. So we have to go through, but this basically just a non-commutative analog of this, whatever I have here. If you have a L infinity sequence and if you have a L1 sequence, then you have this inequality. This is the non-commutative analog of that. Now, in the proof, you have to go through all this is because of non-commutative. Okay. And how I proved is the following. I took trace of ST, then I applied the Cauchy-Schwarz inequality. Yeah, Cauchy-Schwarz inequality for the Hilbert-Smith inner product by taking ST power half, T power half. But to take a T power half, I have to insert a partial isometry from the polar decomposition. So finally, everything went away and finally we got this. Okay. I have written all the details. Trace of ST equal to trace of SU mod T. And I have just written it like this. Then I just applied the Cauchy-Schwarz inequality. Inner product of xy is less than or equal to norm x times norm y. I have taken the square to get rid of the square root. So then finally got this. Okay. If you want me to repeat anything, you tell me. Something in the chat. Oh, so actually, I just looked at the internet and then get it. I mean, there is no really any. I mean, Sundar's book has all these things, has dealt with all these things. But he starts with Hilbert space, Hilbert-Smith operator, and then goes through all this trace class and other things. Okay, and if something is not clear, you ask me. I have just written everything clearly. Okay, or you can read the Sundar's book or any other book. There are several books about deals with trace class operators. Okay, and there are several notes available in the internet. Anyway, if I will tell you something, some reference in the next class. Okay. Okay. So finally, we want to prove the following. For T in B1H, we want to prove that the collection of trace class operators form an Banach algebra. That's what we want to prove. A proof of proposition. Okay, so first, so you can see, we have defined the norm to be like this. Okay, this is the norm. And you can take an alpha. If you multiply T by alpha, then you can take out the alpha. And so you have to prove only the triangle inequality, right? And positivity is clear because of this. So norm, we know that norm T1 trace norm is greater than operator norm, right? We have proved this. Norm T is less than or equal to trace of mod T for T positive. Okay. So because of this, and the norm of norm of any operator, because norm of T is equal to norm of mod T. Okay. Okay. Norm of T equal to, this is just C-star identity, okay, which you have proved already. Because of this implies if norm T1 is equal to 0, implies norm T equals 0, implies T equals 0. So the norm is positive now. We have to prove the triangle inequality. So this is where the U star comes, and I got confused with that. So to prove the triangle inequality, I want to prove the following. I want to take this S plus T. See, here the problem is the following, as you can see. I want to prove that to prove triangle inequality, we have to prove the following. Trace of mod S plus trace of mod T. This is what I have to prove. But the problem here is, this is not true. I mean, there is no connection between these two things. I mean, this is something like S plus T star S plus T. Okay. And so, I mean, square root of this. And that is something S star S square root of that, T star T square root of that. And this S and T may not commute, and you have no relation between them. Okay. So because of that, we have to go through the polar decomposition. And then there is no other way to handle this. You see, there is no linearity or anything. So get the linearity, we go through the polar decomposition and we use the lemma. Okay, so we do the following. So let S plus T is equal to some U star S plus T mod S plus T. Sorry, U S plus T. U times mod S plus T. Be the polar decomposition. System, right? Then this implies mod S plus T equal to U star S plus T. See, this is to get the linearity, and trace is linear, and we can get out. I mean, take this out. So trace of mod S plus T equal to trace of U star S plus T. Okay, this is a bracket. So that is equal to trace of U star S plus trace of U star T. Now this is less than or equal to trace of, sorry, norm of U star times trace of mod S, right? Plus norm of U star trace of mod. Okay. Now U star norm of any partial isometry, I mean non-trivial partial isometry is 1. Okay, so a partial isometry is isometry on some subspace and 0 in the other subspace. You have a big Hilbert space that can be decomposed into 2 orthogonal sum, and a partial isometry is isometry on one of them and it's 0 on the other one. Okay, there is something called initial space, final space. It's an isometry between the initial space and the final space. If you go through all those theorems, it will be clear. Okay, so now this is equal. This is equal to, in fact, but you can write it less than or equal to trace of mod S plus trace of mod. Then this is what we want. Okay, so the triangle inequality is 4. Okay. Okay. So we do the same thing for the Banach algebra also. Now let ST. So this is for S and T, and this is for S and T. Okay. Similarly, if S and T is in B1H, then ST equal to, again, used maybe W star. W star, no star. I don't know the star, obsession with star, I don't know. It is times mod ST. Okay. ST equal to W times ST. Because I have to get the star here and okay. So this implies mod ST equal to W star ST. This is the polar decomposition. Okay. So this is equal to ST. Okay. Now trace of mod st. This is norm of st1 equal to this trace of mod st. That is equal to trace of w star st. Okay. Look at that. This is okay. This is equal to trace of. So we have already proved that. I mean, you can. I mean, this is of course positive, so you can take the mod if you want. This is less than or equal to w star s, norm of w star s, trace of mod t, right? Okay. Now this is equal to norm of, this is less than or equal to norm of s. Norm of w star is 1, so you can write it like this, trace of mod t. Okay. Now norm of s is less than or equal to trace of mod s. Okay. Now this is equal to norm of s1. So the Banach algebra inequality is satisfied. This is the Banach algebra. Okay. Finally, we have to prove it's complete. It's a Banach space. Okay. So to prove B1H is complete, with respect to norm. So let Tn be a Cauchy sequence. Cauchy sequence. Okay. Then we know this Tn minus Tm, norm 1 is greater than or equal to operator norm. Okay. So this implies Tn is Cauchy in norm. Cauchy, here it is in norm 1. Okay, so it is Cauchy in norm, the operator norm. So there exists a T in B of H such that Tn converges to T in operator norm. We have to prove that this T is trace class and Tn converges to T in the trace norm. That's what we want. So as we have done in the earlier case for Hilbert-Smith, to prove the completeness of Hilbert-Smith operators, we approximated using finite rank operator. So let P be a finite rank projection. A finite rank projection. Then we consider this norm of P Tn minus T norm 1. Okay. Okay. Which is equal to trace of P mod Tn minus T, right? Trace of this. So now Tn converges to T in norm. This implies Tn minus T star Tn minus T. This converges to 0. I mean, norm is a nice topology. Norm topology is a nice topology. It's continuous with respect to star. It's continuous with respect to adjoint. It's continuous with respect to products. And the square root is also a continuous function. Okay. Square root is continuous. Was it proved? Okay, I will prove it in the next class. I will check whether it is proved. Otherwise, I will prove it in the square root is also a continuous function. I don't know. I will check. Okay. How do we prove that? I mean, there is a, if you use, there is something called functional calculus. If you use that, that is easy. But without that, how to prove? Let me see. Okay, so for the time being, you assume that square root is continuous. So I'm saying that mod of Tn minus T, okay, converges to 0 in norm. Okay. So mod of Tn minus T converges to 0. Tn minus T converges. This is operator. This mod of Tn minus T is an operator, which is just the square root of whatever I have written in the previous line. Okay, so that converges to 0 in norm. So this implies mod of Tn minus T xx converges to 0 for all x, right? So in particular, you can take finitely many of them, finitely many operators. So that is precisely equal to this. I want to do something else. Tn minus Tn, I want to write. Okay, let all these things be here. I will do the following. I want to talk about trace of P times mod Tn minus T. Okay, that is equal to trace of P Tn minus Tm. Let's see. Limit over here. This is true because Tn minus Tm goes to, Tm goes to T in norm. So because of that, this is true. For each n, Tn minus Tm goes to T in norm. So by the same argument, it goes to this. Okay. Is it okay?
The first line is P mod Tn minus T or normal?
Let me write it clearly. This is what we are talking about: P mod Tn minus T. Okay. We want to say that trace of mod Tn minus T goes to 0. Okay. But but then that's an infinite summation. So I'm hitting it with a finite rank projection P like this. Then I'm saying this is exactly equal to limit. See, this is true. Since inner product Tn minus Tm, okay, xx, okay, this goes to inner product Tn minus T x comma x, okay, as m goes to infinity, right? Okay, and assume that square root is a continuous function, okay, which I will.
Second one, mod of Tn minus Tm.
Mod of
In the second
next line, I have taken limit m with instead of t, I have written tm. Oh, here mod, you are right. Sure.
Yeah, mod.
Yeah, sure. It is mod. Yeah, this is mod. Correct. Good. The bracket is here. Okay. 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 Now, what is this? This is the summation over finitely many of these ENs or whatever. You can take an orthonormal basis for this range of this projection P and extend it to an orthonormal basis with the orthogonal complement. So this whole thing is less than or equal to lim sup of trace of mod Tn minus Tm. The lim sup is over here. Okay, this is true for all. Okay. So this implies trace of Tn. So this is true for all n and for all p. So if you take an infinite series, then for any finitely many of them, it is smaller than that. So because of that, Tn minus T is less than or equal to, this goes to 0. That will actually imply, it's an exercise, that will actually imply that T is in BMH. Okay. I mean, if in the norm, if it goes in the norm, it has to be in T, it has to be in T has to be trace class operator. Okay. So any question? I have to prove one more thing. The one more thing is I have to prove that the dual of trace class operators B of H. We have proved that Hilbert-Smith operators is a Hilbert-Smith, so its dual is its own. So I have to prove that I have to prove two things. I have to prove the two things. Dual of L1 is dual of compact operators. So it is precisely this. It is precisely the analog of this. C0, the all sequences converging to 0, its star is L1. Okay. And L1 star equal to L infinity. Okay. So this translates here. I mean, the analog of this is K of H. That is the sequences converging to 0. The star is B1H. Okay. And B1H star equal to B of H. This is slightly long to prove. I'll prove it in the next class. Okay. So this is what I want to prove in the next class. Now I will stop. I mean, there is some more time, but if I start, there will not be time to finish. I want to do it together. I will prove in the next class and stop. And we can have one more class to discuss if you have any doubt. Okay. So if you have anything, you want me to repeat anything, or if something is not clear and I haven't said it clearly, you can ask me now to go through. Okay. So next I want to prove this. Then I will prove say something about integral operators, which we have already defined integral operators, and say something about that. And the course will end. And we can have one more class just for discussion if you have anything to discuss. Okay. So if anything is not clear, you can ask me. I'll stop recording.